Hello math fans, continuing my series on pancake cutting and recapping a project I made for my honors calculus students back in 2010, 2011, 2012. Ultimately, I kind of changed that project each year, but by the end I had focused on some particular questions, which were these. Can you cut up a pancake into 9 pieces? How do you cut up a circular pancake into thirds? And then I later remembered that there was this bakery, this breakfast place I went to in Pullman when I was a grad student that had spherical pancakes that were called these Aebleskivers. So these Danish pancakes, now they kind of would be called cake pops almost. But I asked students, how would you cut that up? This is just part of this. I was just trying to get it gave us a chance to use some Calculus 2 skills and also practice this idea of generalizing, which is another big thing we do in math. We sort of see a pattern. We try to extend it. We see if we can make it more general. We see if we can make it answer more questions. It's the natural way of how we go. So I'm going to continue this discussion here, building towards the next video will be much more mathematical in general. But I wanted to do a quick recap. And I'll also do some visuals, kind of to recap everything we've done so far and pave the way for a discussion of what do I mean by more dimensions and try to demystify that a little bit. So I found this found my research I did with this student, and this was part of our write-up. So you'll see that this matches what we did in the last video. We ended up solving this equation. This was after we integrated. We set it equal, we had a solver, and this was the number we found last time. And the conclusion was that no matter what the radius is, but let's just say the radius is 1, you need to go 26% of the way over to make your cut. That was the conclusion. So here it would be at 0.26, wherever that would be, maybe there. You make this little cut, 0.2649, and you'd make a similar cut on the other side, negative 0.2649. So that was that piece. I think I will show a quick visual before I explain what's going on there on the right. So a quick visual. Here's what we did last time. I didn't think to put these visuals in the last piece, but we were trying to make these 3 areas equal. I have the areas being computed here. A third of the area was 1.04, and so that's what we were aiming for. And you can see that's too skinny if A is and you got to remember the number was 0.26, and if you make it this far, it's definitely going to be too big in the middle. So somewhere in the middle they all match up, and I have it computing the areas here. This is the area on the right, this is the area in the middle. So somewhere in the middle it happens, and we solve for that. And it was that. It's kind of surprisingly close to the middle, but this is bigger here. So it makes sense that you have to be a little closer to the middle to make all this happen. And it was at that 0.264. If that's what the number was, let's take a peek. 0.265 is closer to what it is. So 0.265. 0.265. So that's as close as we can get in this scheme. You can see we're accurate there. But if we want to be more accurate, we found it exactly. And it does look almost too skinny, but again, imagine shaving this a little bit and pasting it on the top. It's pretty close, surprisingly close to the middle. I think if I was trying to convince someone I was going to cut up a cake that way, it looks like the person who's getting the middle piece is getting the smallest. But yeah, that's not the case. Okay, so we are now going to try to extend this idea to 3D. And we're going to cut up a sphere into thirds. And we're going to ask where that would be so that we can make that happen. So we're going to cut this sphere into 3 shapes, with a big cut. It's going to look like, the middle piece might look like this. There we go, except it'll be filled in. And then the outer piece and so on. So the question is where those cuts are going to be to make that happen. And as we move this, how can we do that? So they're equal. And one question you could ask yourself is, do we think it's going to be bigger or smaller than this 0.26 we had here? Do you have to get closer to the origin or further away as you go to 3D? Just to ask a random question. And you might make a conjecture about that. Okay, so let's go do the computation. This is actually a much easier math problem, surprisingly. And I'll do this using the so-called Math 125. This is really for my Math 125 students. Now, ultimately, these pancakes, I encountered them in this old European bakery, a mainstay in Pullman, Washington, for a good hearty breakfast. This is one of the things they make. It says a Danish pancake that they brought over when they immigrated in 1908. It literally means apple slices in Danish, but apples are no longer a main part of the ingredient. What I remember is you could get it with like a syrup or powdered sugar. You could get it with different types of, cream cheese or whipped cream or something. Or you could even get it with like a berry type mixture. So it's more of a dipping pancake. And things like this are more common now, but I think that was really a novelty. Okay, so now let's ask ourselves what happens when we cut this up. So I'm going to do the Math 125 approach. This is really for my Calculus 2 students. And we have a spherical pancake, and the Math 125 approach is to turn it into a 2D problem and use either one of two approaches, which we learned. One was cross sections, and another was this method called shells. And I might just set them both up because it's good for my calculus students to get a review. So what we did is we said, okay, we have this sphere. Let's say of radius r. We'll try to do a general approach again. And what we're going to do is we're going to turn it into a 2D problem, a revolution problem, such as this. And we could think of it as a revolution problem that way or this way. It doesn't matter. Maybe it's a little easier to think of it this way so that it's more natural to use x. But both ways are really equivalent here. Okay, so if you're going to find the whole volume, your first job is to describe a point on the edge. This is very similar to what we did in 2D. And here we would have x squared plus y squared equals r squared. And then depending on which variable you want to use, and that's really where the two methods come from. So one method comes from what if you want to use x, and another method comes from what if you wanted to use y. And in this scenario, if you're going around the x-axis and you're using x, that's cross sections. And if you're going around the x-axis and you're using y, that's shells. And it boils down to this one piece, which is labeling how you want to label it. So let's draw this circle. Da-da-da. Terrible circle. But we can, and I should have labeled where our goal in this problem is to cut it into thirds. So let's pretend we have this plane. I'm just drawing the side view of the plane that's cutting through it at x equals a. So this is x equals a. And let's just examine what happens when we rotate this around. So we want that volume, the resulting volume of that. And you can also do it, like I said, you can do it in terms of y. It's going to look like this. I'm pretty sure when I did this for my honors class, we did it in terms of x. So this will be the first time I've done it in terms of y, but it's a good bit of review. So let's consider this region. If you do it in terms of x, your job, just to recap for my students, is to label a random x in the region and find a pattern based off of x. Some things you would label is, what if I have, a tiny little bit of thickness, you can take, and then you can label this length. In particular, this y value is going to be whatever you get when you solve for y here. So it's the square root of r squared minus x squared. We did that in the last video as well. And that is what we'd call the radius of a cross section, because the cross sections are what we call discs here. It turned out the method is to do the integral from a to r of the area of a cross-section. And here the radius of the cross-sections are how far it is from the axis of rotation to the edge of the circle, which is this square root of r squared minus x squared dx. And the reason this is easier than the 2D example is because the square root and the squares cancel. So it leads to a much easier integration, and you don't need trig substitution. And that's really the way to go. But if you're someone that wants to review shells, the shell method is to try to do it in terms of y, but that requires you to label these two things. So you would solve for x. You would label this x, which is x equals a. And from that, you would think about the cylindrical shell that is formed by that piece. You would say the integral from y equals, we'd have to solve for y. Y equals 0 to wherever this is. That x is a. And if x is a, y would be the square root of r squared minus a squared. So again, if this is, you can skip this part, y square root of r squared minus y squared dy. So either way would be fine. This actually can be done with substitution, so it works out okay. But to me, this looks better. Now, the hardest part here is to realize that r and a you're treating as constant. So when you go to integrate, you're going to get pi r squared x, because r squared is being treated like constant, minus 1/3 r cubed from a to r. And then ultimately, you got to remember, our plan is to try to make that equal to 1/3 of the volume. So we have pi. When I plug in r here, I'm going to do r cubed minus 1/3 r cubed from plugging in r in here. So that's going to be 2/3 r cubed. Good to simplify as you go. Hopefully you've gained that from me a little bit this term. Minus r squared a minus 1/3 a cubed. And here we got it. It's pi times 2/3 r cubed minus r squared a plus 1/3 a cubed. And we want that to be equal to 1/3 of the area of a circle. And the area of a circle is 4/3 pi r cubed. So I'm relying on us looking up that formula. So this equation is quite a bit nicer to solve. There's no inverse trig. It doesn't have some of the challenges we faced in the last one, except for the fact that you have the same issue with the a's and the r's. This is where generalizing sort of helps, because in the previous one we saw that if we divided in a clever way, we could, instead of solving for a or r, we solved for a over r, that percentage. And I don't think I would have thought of that here unless I had already done the previous case. So I'm going to divide everything by r cubed, and some nice things happen. In addition, you can divide everything by pi. So there's several little bits of cleanup we can do. So let's divide everything by pi. Well, that's lovely. Let's divide everything by r cubed. So we're going to get 2/3. As I say in a previous video, we're taking a sad song and making it better. We're cleaning it up. This is going to become a over r, because you're going to put an r cubed. 2 of the r's are going to cancel, and you're going to be left with an r. And if you aren't following, try it on your own. And then you're going to have an a cubed over r cubed. And that's going to be equal to 4/9. And you see that a over r appearing right here. And so then you can say, I'm trying to solve 2/3 minus t, let's call that t, plus 1/3 t cubed equals 4/9. I don't know if I did this back then, but I would be very tempted to multiply everything by 9, because I hate fractions when I'm solving, and if I can multiply both sides by the same thing. So if I multiply by 9, this will become a 6, this will become a 9, this will become a 3, this will become a 4, and you get this cubic equation. And maybe that's a topic for another video. How do we solve cubic equations in general? But I'm just going to use a solver. And you can solve for t, and that will solve for every possible radius. So I'm going to now peek at my solutions, because you can see I did this. That'll also catch. This is the paper solutions I wrote back in 2013 when I first did this problem. I haven't looked at them since. So we want 1/3, so you can see that same setup. You can see it's 1/3 of the volume. You can see I integrated. You can see we simplified. Oh, why didn't I multiply times 9? See, I disagree with myself here. In my last video, I thought I was smarter back then, but now I don't know. Wisdom would win out, because I definitely would multiply everything by 3 here, which would give us this equation. In any case, I put it in a solver, and I got 0.22607. So 22% of the way. So do you remember the number for circles? You were 26% away from the origin and towards the radius, and now we're 22%. So you're a little closer. Let's go take a look. So that's 0.226. Let's go take a look at our visual. So again, in this case, we had to be 0.26 away. Now I know everyone's asleep. But here we have to be 0.22. 0.22. Right there. And it gets exactly half. So it's kind of interesting that it gets closer. And I considered the matter closed. I was kind of pleased that I had taken my little pancake, cutting up Egos for my kids, and turned it into a project, and that students had found it mildly entertaining, maybe, or they pretended to, so that I'd write easier tests. You know, it doesn't help to brown nose a little bit. And then I had the next year turned it into a problem where we got to generalize it. So I was happy with that. And we saw some of these same things happening. That was fun. And then a year or two later, one of those students came back to me and said, I would like to write. They had studied a little bit of higher dimensional calculus. They'd gone on and taken a few more courses. And they said, I'd like to generalize your project to multidimensional hypersphere. So that's the one and only time I've ever mentored a student on research. And I think I did a bad job of mentoring. I apologize. I'm going to apologize to that student in the next video. But it was, a chance. It was funny that they latched onto this question. So before we do that, I thought it would give us a little primer. If you're going to go higher, some of this is going to be tougher. So before I do that in the next video, let's talk about a few things and summarize. So what we did first was we found the area, and we did this question. So I'm going to just set the stage for the next piece. So we had this line right here, x equals a, and we had this circle, x squared plus y squared equals r squared, and we were solving for when that was 1/3 of the area. Now it turns out area can be viewed, and at least we found that it was easier to generalize in this way, as a double integral of 1. So this is more of a 1/26 approach. And it turns out that volumes, and I'll explain that a little bit, because again, most people watching this are my 125 students. The volume of this little piece out here that we chopped off, I don't know what, this cap of a sphere that would be here. We can view that, and this is not just that volume, but any volume, as what we call a triple integral. And basically it comes down to describing the region. This is more general than just a volume of revolution. So anyways, you just describe the region. It's the same skills we've been learning in Math 125, which is what's the biggest and smallest x can be. Well, x can go from A to R. So the game I play with students is I make them hit a buzzer. I walk across here, and I kind of lightly drag my pen, and I say, when I hit the region, hit the buzzer. And I keep walking, and I mow the lawn, sometimes I say. And then when I get to the end, hit the buzzer again. And those are the bounds here. Those are the bounds for x, we say. And it works like a nesting egg. And then you say, okay, once you're in the region, we call it an iterated integral. Once you're in the region, we say, how do you mow the lawn? Meaning, if I'm taking a lawnmower and I'm about to mow the lawn, when do I turn it on and when do I turn it off? And then when do I turn it on and when do I turn it off? And when do I turn it? We need a pattern for each X for when I turn it on and turn it off. Well, I turn it on and turn it off when I get to the top and bottom of this. Basically, when y equals plus or minus the square root of r squared. And this should sound familiar to what we actually did, but those become the bounds in a double integral. Instead of it being top minus bottom, they become these bounds. So this is a little preview of Math 126 and double integrals. Double integrals in our Math 126 course happen in chapter 15. dy dx. And that looks worse than it is. It turns out you integrate it just like you normally would. This would become a y because we're going to respect to y. You evaluate it at these two pieces, square root of r squared minus x squared, square root of r squared minus x squared, and then you plug those in, and when you're done, you integrate with respect to x. That's why it's called an iterated integral. And you should notice that when you plug that in, you're going to get this minus the negative, so you're going to get 2 times the integral from a to r of the square root of r squared minus x squared, which is the same thing we got before. The reason I'm saying this is easier to generalize to higher dimensions because you can, without having to adapt or think of top bottom, we can naturally extend this. Okay, so how do we naturally extend it? Well, when you get to 3D, you ask yourself the same questions. You say, what's the biggest and smallest x can be? Well, the smallest x can be is a, and you just do it the same way, except you have 3 axes to walk along now. So if you consider this solid that we're talking about, that's over here, and apologies, I know I'm not the best 3D drawer, but I have found not very many people are. So let's draw even bigger. So we have, here are these axes. And here is x equals a, and here is x equals r. Okay. And here's how we describe it. So you're always between the upper hemisphere and the lower hemisphere. So I think when I teach Math 126, this is actually beyond Math 126, but we talk about the sphere, and the equation of the sphere is x squared plus y squared plus z squared is r squared. It looks exactly like the equation of the circle, and it has to do with distance in the same way, distance on a straight line. If you solve for z, you get the upper and lower hemisphere. And so you get the square root of r squared minus x squared minus y squared. And you get negative the square root of r squared minus x squared minus y squared. And that says, if you give me any space on the ground, let me draw a picture of the ground here. Maybe it looks like this. If you stand anywhere on this plane right here, and you look up, or you look down, this is how far you can go before you hit the upper or lower hemisphere. So in Math 126, we're talking about what I always draw, and they look like flying carpets, but we're talking about what we call surfaces, and those are given by a function of 2 variables. And that's what these are. Those are surfaces that tell you how high to go. This isn't quite mowing the lawn because it's in 3D. So we say, okay, this is how high you can go. And then we're back to describing something in 2D. Now we'd like to talk about all the places we can stand. And this will look exactly like this. So it'll look like negative the square root of r squared minus x squared. And you can start to see how maybe we can generalize this. And then we say dz, dy, dx, and then we iterate an integral, and that will give us the same thing that we got here. In both cases, after we did all the integration, we replaced x over r with t, and then we solved for t. And in the first case, we got t was about 0.26. And the second case, we got t was about 0.22. Okay, so the next video I'll talk about what this student did. Again, it wasn't me pushing this research. I haven't worked in higher dimensions. They just wanted to ask this question because they'd read some papers on this. So we're going to travel into the higher dimension, which sounds mysterious. What we lose is the ability, the idea of many dimensions doesn't have to be sci-fi. You could have a business that sells 500 products, and so your profit function would be a function of 500 variables plus the output, which is your profit. So if you wanted to graph it, you'd have to graph it in 501 dimensions. But I imagine that business doesn't think they're doing anything sci-fi. They're just selling stuff. So the fact that you have multiple variables doesn't have to make something mysterious. But if you want to define geometry concepts and multiple variables, then you have to be precise about what you mean, because you're not going to be able to look at them. Okay, so I'm going to end that there, and the next one will be a different sort of video. All right.